Hello everyone, welcome back to my channel. In this video, I'll tell you how to implement 2-bit comparator using ROM, PLA and PAL. But before that, I request you all to subscribe to my channel. Also at the end, if you feel this video was really helpful, then share this video with your friends and press the like button. So 2-bit comparator means it compares inputs. So it has two inputs and both inputs are 2-bit inputs. So length of A and length of B both are 2 bits. So when it is comparator, it means its outputs are either A less than B, A equals to B or A greater than B. Then here ROM, PLA and PAL, all of them are programmable logic devices. It means single IC can be used for multiplication of many circuits. So here in case of ROM, see, when we implement any circuit, any digital circuit, either we can implement it as sum of product form or product of sum form. And in all forms, what we need is AND gates and OR gates. So in case of ROM, it has fixed AND array. It means AND gates are not programmable, they are fixed, whereas OR array is programmable. In case of programmable logic array, PLAs, both AND and OR, both of them are programmable. And in case of PAL, programmable array logic, AND gates are programmable but OR gates are fixed. So let's start with the truth table. So see, inputs are 2, A and B. So A is 2 bits, so A will have A1 and A0, 2 bits, and B will also have B1 and B0, 2 bits. So total we have 4 bits and outputs are A less than B, A equals to B, A greater than B. And when we write truth table in binary number system, it is 1 0, 1 1, 2, 4 and 8. So here I'll write 8 times zeros and then 8 times 1, then 4 times zeros, 4 times 1. Truth table for 4 variables. Now I'll compare A and B. So see here, A is 0 0, B is also 0 0. It means A is equals to B. So A is equals to B is 1 and remaining 2 are zeros. Then 0 0 0 1. It means A is 0, B is 1. So A less than B. Then 0 0 1 0. Again A less than B. 0 0 1 1. Again A less than B. 0 1 and then 0 0. It means now A is greater than B. So 0 0 1. 0 1 0 1. Both are 1. It means A is equals to B. 0 1 0. 0 1 and 1 0. 1 0 is 2 and 0 1 is 1. It means A is less than B. 0 1 1 1. Again 3 and this is 1. So A less than B. 1 0 0 0. So here A is 2, B is 0. So A greater than B. 0 0 1. 1 0 0 1. Again A is greater than B. 1 0 1 0. Both are 2. So A is equals to B. 1 0 1 1. So this is 2, this is 3. So A less than B. 1 1 0 0 is A greater than B. 1 1 0 1. A greater than B. A greater than B. And here also here 1 1 1 1. So A and B both are same. So A equals to B. Let's find out min terms for A less than B is equals to summation of M. A equals to B. A greater than B. Okay. So here I'll write min terms, the names. This is M0, then this is M1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and this is 15. So for A less than B, 1, 2, 3, 6. What we are doing? We are selecting values which are 1, 7, 11. That's it. For A equals to B. For A equals to B, 0, 5, 10 and 15. And A greater than B is 4, 8, 9, 12, 13 and 14. So these are the min terms for 3 outputs. So let's start with the implementation using ROM. ROM is also called as one-time programmable PLD. So here we are going to implement 2-bit comparator using ROM. Whenever we implement circuits using ROM, what we use is decoder. Here how many inputs we have? We have 4 inputs. 2 bits of A and 2 bits of B. So total inputs are 4. So we need to take 4:16 comparator. Decoder. See, in case of decoder, number of outputs are 2:n and here n is equals to 4. So that is 16. So I'll first draw 4:16 decoder which has 4 inputs and 16 outputs. So this is my 4:16 decoder. Here inputs are A1, A0, B1 and B0. And I have total 16 outputs. I'll mark them as 0, 1, 2, 3. Okay, so total how many outputs we have? We have 3 outputs. A less than B, A greater than B and A equals to B. So I'll draw 3 OR gates. My first OR gate. This is A less than B. This is A equals to B. And this is A greater than B. Now we have equations for these 3 outputs. These are our equations we got from the truth table comparison. So for A less than B, values are 1, 2, 3, 6, 7, 11. So here OR gates are programmable, and to represent programmable input we need to mark cross 1, 2, 3, 6, 7 and 11. For A equals to be 0, 5, 10 and 15. And for A greater than B, 4, 8, 9, 12, 13 and 14. And this is implementation of 2-bit comparator using ROM. Now let's see how to implement using PLA and PAL. For implementation using PLA and PAL, we need to find out equations in sum of product form. So what we have min terms. Let's put these min terms into K-maps and let's find out equations. We have 3 outputs, so we need 3 K-maps, and you can see number of inputs are 4, so we need 16 cells K-map. Here inputs are A1, A0, B1, B0. See, you need to follow this sequence. Here it is A1, A0, B1, B0. In K-maps, we use gray code, and that is why 0001, then not 10, it is 11 and then 10. Then see, when you will see 0000 is 0, 0001 is 1, 0011 is 3, 0010 is 2, 0100 is 4, then 5, this is 7, 0111, this is 6, here it is 1100 is 12. So it is like you need to go to last row 1 0 0 0 is 8. So after 7, 8 comes here. 9, here goes 10, 11, 12, 13, 14 and then comes 15. So here first column, second column, then last and then third. Similarly for rows also 1, 2, 3 and then 4. Okay, so let's put values of A less than B here. This is my A less than B. So for 1, it is 1. For 2, it is 1. For 3, it is 1. For 6, 1. For 7, 1. And for 11, 1. And at other places, it is 0. So you can put from these min terms or you can put values from this table also. So it is first 4 are, I'm writing for A equals to B 1, 0, 0, 0. Then I'll make groups of 4. Then 0, 1, 0, 0, 0, 1, 0, 0. Then 0, 0, 1, 0, 0, 0, 1, 0. And then 0, 0, 1, 0, 0, 0, 1. Similarly for A greater than B, first 4 are zeros, then 1 0 0, then 1 1 0 0, 1 1 0 0 and then 1 1 0. Now we have substituted all the values. Now let's group them and let's find out the equation. Okay, so let's start grouping. So here what we can do, we can make groups of either adjacent ones or overlapping one. So I have these 4 ones. So I'll make chord. For this one, I don't have any adjacent one. So I'll make group with this overlapping one. And for this one, I'll make this pair. And here I'll write equation for A less than B. It is for this pair, A1 is 0. A0 is also 0. So A1 bar, A0 bar. And here B0 is 1. B0 is common. So B0 plus for this chord, here value of A0 is different. A1 is 0. So A1 bar and here B1. Similarly for this pair, what is common in these two is value of A0 is 0. So A0 bar and here it is B1, B0. B1, B0. This is my equation for A less than B. For A equals to B. Here I don't have any adjacent or overlapping one. If you reduce it, you will get equation in terms of XOR gate, but I'll write it in terms of AND and OR gates because I'm going to implement using PLA and PL. So for first pair, for first one, this is for A equals to B. For this one, it is A1 bar, A0 bar, B1 bar, B0 bar. A1 bar, A0 bar, B1 bar, B0 bar. Plus for this A1 bar, A0, B1 bar, B0. B0 is 1. So whenever it is 1, we take variable as it is. For this one, A1, A0, B1, B0. A1, A0, B1, B0. Plus for this one, A1, A0 bar plus, not plus, into B1, B0 bar. B1, B0 bar. This is my equation for A equals to B. Now last is A greater than B. Here I can make this chord group of 4s. For this one, I'll make this pair, and for this one, I'll use overlapping. Overlapping means what? If I'll fold my K-map from here, this one and this one will get overlapped. So I can make group of them. So for first chord, For this chord, equation is, here what you can see, A1 is common, it is 1. So A1, and here B1 is same, 0. A1, B1 bar. Plus, for this vertical pair, it is A0, B1 bar, B0 bar. Plus, for this pair, it is A1, A0. And what is common in these two? B1 is 0, 1. So, can't take B1. B0 is 0, 0. So, B0 bar. So, let's start implementation using PLA. Here, we have 4 inputs. So, I'll connect those inputs through buffer so that I'll get true terms as well as complements of them. So, I'll take A1 first, then A0, B1, and then B0 through buffers. Buffers will generate true and complement form. So, this line is my A1 with bubble. This line is my A1 bar. A0, A0 bar, B1, B0 bar, sorry, B1 bar, B0, B0 bar. The best part of PLA is both AND gates and OR gates are programmable. So flexibility is highest in this PLD, but the thing is they are slower because all are programmable. So how many AND gates we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So total we have 10 AND gates. So I'll draw 10 AND gates here. So I'll draw for all AND gates first. So these are my 10 AND gates. Now I have 3 outputs. So I need to take 3 OR gates. And they are for A less than B. This is for A equals to B. And this is for A greater than B. And then I'll program them. Programming means we need to connect to specific inputs. Inputs to our first AND gate are A1 bar, A0 bar and B0. So this is A1 bar, A0 bar and B0. For second AND gate, A1 bar, B1. For third AND gate, A0 bar, B1 and then B0. Here A1 bar, A0 bar, B1 bar, B0 bar. So A1 bar, A0 bar, B1 bar and then B0 bar. A1 bar, A0. A1 bar, A0. B1 bar, B0. B1 bars. This bubble indicates bar. This is true term. This is B1. B1 bar, B0. Next is A1, A0, B1, B0. A1, A0, B1 and then B0. And last is A1, A0 bar, B1 and then B0 bar. Similarly, for A greater than B, it is A1, B1 bar. A1, B1 bar. A0, second AND gate is A0, A0, B1 bar, B0 bar, B1 bar, B0 bar. Then A1, A0, A1, A0, B0 bar. So these are programmable inputs to my AND gates, programmable inputs to my AND gates. Now in PLA, this is implementation using programmable logic array. OR gates are also programmable, and to represent programmable input we mark cross. So for first A less than B, there is addition of first 3 AND gates. So these 3 AND gates, their outputs will go to first OR gate. For second A equals to B, addition of these 4 AND gates. And for A greater than B, addition of these 3 AND gates. And this is implementation of 2-bit comparator which has inputs A1, A0 and B1, B0 using PLA. You need to remember, in PLA and in PAL we have AND gates and OR gates. Here both AND and OR array is programmable. Now let's see how to implement same circuit using PAL. See, one more thing is, in PLA it is possible or it is allowed to have different inputs to OR gates. Like for first OR gate there are 3 inputs, for second OR gate there are 4 inputs, and again there are 3 inputs. But in case of PAL, when we implement using programmable array logic, inputs to OR gate are fixed. It means all OR gates will have either 4 inputs or 3 inputs. It is not possible that first OR gate will have 3 inputs, second will have 4 inputs. So we need to take OR gates with 4 inputs, because maximum what we want is 4 inputs. So let's see implementation using PAL. These are my 4 inputs. This is A1, A1 bar, A0, A0 bar. Through bubble we get bar. Okay, so now we have equations for A less than B, A greater than B and A equals to B. So how many AND gates I need? I need 12 AND gates. Here, as I told you, we must take 4 input OR gates, because here I want for one term I want 4 inputs. So for every other term I'll have to take 4 input OR gate. So I need 4 3s are 12 AND gates. So first I'll take 12 AND gates. So I'll draw 12 AND gates here. So these are my 12 AND gates. Now you can see here from these equations, in A less than, how many AND gates I want? I want only 3 AND gates. But because my OR gate need 4 AND gates, that's why I have drawn this, but I'll not use it, but I'll have to draw it. Then similarly for A greater than B, again I need only 3 AND gates, but I'll not use this AND gate. Now let's draw OR gates. How many OR gates we need? 3. One is for A less than B, one is for A equals to B, and one is for A greater than B. See, in few books you may find that not like this. OR gates may be drawn here only and these fixed inputs are connected to them directly. This process is also correct and this method is also correct. I'll show you how we represent fixed inputs. But here you can draw and then you can connect directly. This method is also correct. Okay, so let's start marking of programmable inputs first. So first term is A bar, A0 bar, B0. A bar, A1 bar, A1 bar, A0 bar, see with bubble we get bar, into B0. Second is A1 bar, B1. A1 bar, B1. Next is A0 bar, A0 bar, B1, B0. B1, B0. And we don't need fourth AND gate. Here A1 bar, A0 bar, B1 bar, B0 bar. A1 bar, A0 bar, B1 bar, B0 bar. Then A1 bar, A0, A1 bar, A0, B1 bar, B0, B1 bar, B0, B1 bar, B0. Then A1, A0, B1, B0, A1, A0, B1, B0. 0. Then A1, A0 bar, B1, B0 bar. And here A1, B1 bar, A1. This is my A1 and B1 bar. This is my B1 bar of it. For second A0, so this is my A0, B1 bar, B0 bar, B1 bar, B0 bar, and A1, A0, A1, A0, B0 bar. And I don't need this fourth AND gate, but because in case of PAL, OR matrix is fixed. It means for every OR gate will have 4 inputs. So we will have to take these 2 extra AND gates. So best part of PAL is because of these fixed OR gates, they are faster, but their flexibility is less. So for first OR gate, there is addition of these 3. So these 4 will go to input of first OR gate. See, to represent programmable inputs, we use cross. To represent fixed inputs, we use these thick dots. Similarly, for second, so this is my A less than B, this is my A equals to B, and this is my A greater than B. For second OR gate, these are my fixed inputs, and for third OR gate, these are my fixed inputs. So this is implementation of 2-bit comparator using programmable array logic, where AND gates are programmable and OR gates are fixed. Then this is implementation of 2-bit comparator using PLA, where both AND and OR matrix is programmable. And here 2-bit comparator using ROM, where AND matrix is fixed, and that is why we use decoder, and OR gates or OR array is programmable. This is the oldest PLD, ROM. The best part of this is OR matrix is programmable, but the worst part is even if we don't use any output, it generates all the minterms or all the AND outputs. So this is how we can implement 2-bit comparator using ROM, PLA and PAL. Thank you so much for watching this video, and don't forget to subscribe to my channel. Also share this video with your friends and hit the like button. Thank you for watching.